Welcome everyone. This is the 5th video of the coil winder building series, and this video will be entirely theoretical. So I will be talking about the technical details, the source code which is on the microcontroller, and some of the calculations which are used to move the stepper motors, especially the feeder, in a proper way. So this source code in fact is a recycled one, because in one of my previous projects I built a universal stepper motor control panel, and basically in this project I'm using a similar control panel, except that the code on it is a bit different, but still I need a display, I need a few buttons, and I need a rotary encoder to see and to be able to change the input parameters, and also to start and stop the motor. So I'm using a Nokia 5110 display. So I'm using a library from this website or GitHub repository, and therefore this line basically is just a copy-paste line. You have to make sure that you use the proper pins which are listed here. And this display is strictly speaking 3.3 volt compatible. Some sellers claim that their unit is 5 volt compatible, but I would be more safe to use the 3.3 volt to power this, and also to use 3.3 volts across the communication lines. So this thing communicates with SPI, so we have to wire it accordingly. And then we have extra stepper library, and we use 2 stepper motors, one for the feeder, and then I use this TB6600 driver for it. And we have the main shaft which holds and rotates the bobbin, which will be our coil, and that is driven by this stepper motor driver. And as I said, we have a rotary encoder, so that consists of 3 pins, 2 pins for the rotation, that is the CRK and DT pins, and one more pin is for the switch. And then we have 2 buttons, which is the up and down button, and sometimes they are used as stop and start as well. And then finally I have 2 output pins, because sometimes you want to enable or disable the power on the stepper motor drivers, so there is no current flowing through the coils of the stepper motors when they are not moving. So therefore you can save power, and you can also save some heating, because sometimes these stepper motors can run pretty hot even if they are stationary. And if you know how the rotary encoder works, then you might know why I use these 4 variables. But in a nutshell, when you turn the rotary encoder, you change the status of the output pins from low to high or high to low. And the change and the transition has to be registered in order to know which direction we rotated and how many clicks are done and so on. So these 4 variables are responsible for this, to register the current and the previous status of a certain pin, the CRK and the DT, and then we do some comparison whenever we triggered the interrupt function or routine by turning the rotary encoder. And then I have a few timers for the rotary encoder and the button, and they are needed because I want to sort of debounce it with the software. And what I do here is very simple. When I, for example, press the button, I immediately start a timer, and while that timer is running, I don't allow the code to register any more button pushes. Therefore, if the button is ringing, or we just accidentally press the button twice, that will not be registered, and there will be only one single button press or one single click from the rotary encoder will be registered. And then we have a lot of variables here. There's a huge list, but don't be scared. It's quite easy because I named the variables according to their role. So this first thing is just stores the state of the button, whether it is pressed or not. And then we have the menu counter. So when we are changing the pages of the menu or changing the menu items, we are in the menu number 0, 1, 2, 3, 4, and so on. And this is where we store this. And you might have noticed that this is volatile. And it is volatile because we can, or not can, but we change this variable within an interrupt routine, and then you have to tell the compiler to store this variable somewhere else, so therefore it is volatile integer and not simple integer. So we have the max speed, and this is for the main shaft, which turns the bobbin, and then for the feeder we don't need this because that will be calculated based on this speed and the other parameters of the coil. And then we have the acceleration parameter, but it's not used in this version of the code because I run the stepper motors without any kind of acceleration, so this can be put into a comment or something. So the feeder speed, this will be calculated based on the parameters as I mentioned. Then number of turns, I have my default value 160, but this will be changed by the user by selecting the proper menu and then changing the parameters value. Number of turns done, we have to keep track of the number of turns while winding the coil, so this variable will store the number of turns done during the winding. Wire diameter, pretty much self-explanatory. I'm using this 0.35 because I'm working with this wire, as you might have seen in my previous video, and therefore it's more easy to just start up with this value and I don't have to change it. Then I have turns per layer, pretty much self-explanatory, so we just calculate the total amount of turns, and we know how much turns we can fit in one layer, and then this is the variable which tells the turns per layer. And then this is the steps per layer for the feeder, so this will set the number of steps in one direction when the feeder oscillates. Layers to do, so this is again self-explanatory, so how much layers we need to do. A number of layers, this is the same as the previous one, but the layers to do is not touched, that's just a calculated value and we just store it. But the number of layers is more like a dynamic value. You will see it in the latter part of the code. Coil pitch is not yet implemented, but this will be useful when you want to have a coil with some custom pitch and you don't want to wind the wires right next to each other. And then this is the physical width of the bobbin, this is the physical diameter of it, this is the total wire length, and this is calculated, and this will be one of the parameters which I will explain in more details how it is calculated. This is the main shaft total steps, so basically when we have the number of turns, then we can calculate the total steps and we have to store it. Then the manual steps for the main shaft is basically used when we move the stepper motor like manually using the buttons or the rotor encoder. And then these two variables are just repeated for the feeder. So we have to calculate the total steps for the feeder, which will basically depend on the width of the bobbin, the wire diameter, and the number of turns. And then if we want to move it manually, the feeder, then we have to use another variable to move it, either with the buttons or the rotor encoder. And then here we have to hard code the microstepping values, and I'm using 1600 for both motors. And then finally we have these stepper button steps. Maybe we can just do it like this. So this is when we move the motor with the buttons. I created another variable. And then we have a bunch of booleans, but these are mainly for keeping track of the position in the menu. So this will tell the code, or these variables will tell the code whether we are in a menu. So for example, we are about to change the number of turns, or we are paging across the menu and trying to find one of the items which we want to change. And then there are some other parameters which will tell the code when to update the screen, when to update just a part of the screen, when we update the value, and so on. And finally here, this tells the code if the winding is running or not. This will be relevant also for some of the calculations. And then these character arrays are for the printing. So we have sometimes strings, sometimes we have floating point numbers, and we want to print them on the LCD, so they will be used, and we are not printing strings directly but character arrays. Direction multiplier, it can be +1 or -1, and this will basically tell the feeder to go in positive or negative direction, so move away from the motor or move towards the motor, and this will help us to oscillate between the two ends of the bobbin. And then the main stepper timer is also a timer which will be used to update the display. So at this moment, as you will see it later, every 1 second I will update the total length of the wire consumed and also the number of turns done. So now we arrived in the setup. The setup runs only once when you start the microcontroller. So here we have all the pins defined as input pins, which are relevant for the rotary encoder, first 3, and the 2 buttons. And then we have output pins, because these are the enable disable pins for the 2 stepper motor drivers. And then we read the status of the rotary encoder right now. So whenever we move the rotary encoder, the next status at that time will be compared to these 2 numbers, or basically numbers 0 or 1, and then the code will determine whether it should do an increment on a value or a decrement. So this is how we do it. And of course the rotary encoder itself, especially or more specifically the CRK pin, is used as an interrupt pin, and whenever there is a change, the rotary encoder function will run. And now we can do something with the stepper motor configurations. So we just set up the initial values, but before we start the real winding, these values will be recalculated. And then we disable or enable the power depending on how your stepper motor driver is wired. Then we have to start the display, and then we print the initial welcome message on it. I also make sure that the microstepping is at the perfect value, so I just once again define them, or not define them, but give the value to the variables 1600. And I made a comment here. So I'm using this SFU 1605 ball screw, and it has a 5mm pitch. So it means that when you do 1 full turn on the screw, then the block on it, or the bearing on it, will advance by 5mm. So if you want to advance 1mm, that is 1600 divided by 5, so 320 steps. And then we can use serial communication, but I was just using it to get the values printed on the serial terminal and to see if I calculate the values properly in the code. So then let's see what is in the loop. And first of all, what happens here is that, as I said, we have a few different variables which will make sure that the information on the display is updated. So this is basically when we changed these variables to true in one part of the code, then in the next iteration of the loop we will enter these functions, and then we will update the display. And you can see that after we did the stuff with the function, we set this variable back to false, which means that the next loop iteration, so when we start to go down on the code, we will not enter. And in this update menu position function, the menu changed equals false is inside the function, so that's why you don't see it in the next line. Then what we do after updating the display, if it's needed, we check the button on the rotary encoder, whether we pressed it or not, and also we do the same with the up and the down button. And then we also check the steps, so this is done when the winding is running. And if we did something either with the buttons, with the rotary encoders, or something has to be done because the checking procedure suggested, we move the stepper motor. And I'm using the run speed to position function, which means that there are no acceleration implemented. because we are moving slowly, relatively slowly, so we don't need to ramp up the motor or the speed, so this is fine. And then here, this is the update of the display value. So when we are in the winding mode, so winding is running, then in every 1000 milliseconds, so 1 second, we calculate the number of turns done, and then we update that value. So that is what is happening here. And now we should look at the functions, and first, since the first function which we have is the rotor encoder, let's take a look at that. So what happens here is that we have a lot of if and else if conditions here, and those are looking at the menus itself. So if we are inside the menu, we do something. And what happens in nutshell, first of all, we read the current value of the rotor encoder, the CRK pin, and then we do a set of comparisons here, which will actually tell us whether the rotor encoder was rotated in the clockwise or counterclockwise position. And based on that, we decrease or increase the value of a certain variable. And what happens here is that if we went in the positive direction, then we increase the value of this variable. And then if we went in the other direction, and if the speed is 160 steps per second, we don't do anything, because this is how I want to, let's say, lock the minimum speed. So we cannot go below this speed. But otherwise, if we are above 160, we let the user to decrease the speed. And then we make this value true. So in the next iteration of the loop, the display will be updated. And then we store the current version or the current value of the CRK pin in the CRK previous variable. And we do the same with all of these, so I'm not going to explain it, but just very quickly this one once again. So we check the current reading from the rotor encoder, and then we do some kind of comparison in these two lines, and then we see that if it was a positive rotation on the rotor encoder shaft, then we increase the value of a certain variable. Otherwise, it was a negative direction, so we decrease the value. And then we tell the code that the value was changed by changing this variable into true. And then we also store the currently read, so what we read here, that will be stored in the CRK previous. And then it's done. And then we have a bunch of else ifs for the number of turns, for the wire diameter, for the coil pitch, but this is not used, as I said, for the bobbin width, and then for the bobbin diameter. And then here I can explain this a little bit more, but still, so this is when you manually move the stepper motor by rotating the rotor encoder. So what happens here? Again, a comparison here. So we decided that this will be the positive direction. So what we do here is that we use the main shaft manual steps variable to store the number of steps which we have to do. And what happens here is that we read the current position. So let's say that is 200 steps. And then we add 160. And 160 increments, that is 1/10 of 1600. So it will be basically 36 degrees rotation on the shaft. So then this happens in the positive, and the negative does the same, except we subtract 160 from the current position. So if this was 200, once again, it will be 40 here, and this will be 360. So then we let the code know that the value is changed. So the display will be updated. We store the last CRK status. So then finally we have this move to function with the main shaft manual steps, so which we recently changed. So then this function will know that we are moving on an absolute scale, and at this moment before moving the motor, we are standing in the 200 steps position. So if we increased by one increment, it will move 160 steps towards the 360 step position. Or if it was decreasing, so we decrease the value by 160, it will move backwards counterclockwise to the 40 steps position. And then we do the same with the feeder shaft. So I'm not going to explain that. And you can see the code line by line and with a lot of commands. So you see it properly. And then winding selected true, we don't do anything there with the rotary encoder. And finally, after the lot of if and else if branches, we have the else. So this means that we are inside the menu, but we haven't selected any of the items. And what this does is that, again, comparison of the different pins, CRK and DT, and then we define the positive direction. And what I do here is basically a ring, let's say, structure. So if the menu counter is below 9, we let it to increase by 1. And if it's 9, then the next value will not be 10, but it will be 0. So we jump back to the first item of the menu. And in the else, where we rotated counterclockwise, it will be the same, but in the other direction. So we go to 0 in a way that if we are above 0, we let the menu counter variable to be decreased. But if we are at 0, the next value will not be -1, but it will become 9. So we go to the top of the menu. So this is how it works. So then let's go through these other functions. So the print LCD is just a welcome screen. That's all. You can write anything here. And then we have a function which is running always in the main menu, or the main loop, sorry. And that is the checking function for the rotary encoder's button. So we read the value, and if the value becomes 0, so we pressed it, but this depends on how you wire it, then we start a timer and we see if the elapsed time was more than 1 second. And if the elapsed time, so since the last button press, more than 1 second elapsed, we let the code to enter this big part. And nothing else happens here is that we take any of these menu item variables and we change its status. So if it's true, it will become false. If it's false, it will become true. And what this does, it will let the code know whether it should enter a menu or exit a menu and go back to the main menu. That happens here. And then we let the user know that the value selection was updated when we change this. And then we restart the timer. And then let me take the opportunity and go to the update value selection menu, because that makes more sense. So this is the update selection. So I just changed the font to a larger font size. And what we do with this lot of if and else if parts is that if the stepper max selected is true when this function runs, then we print this larger symbol there. So this indicates that the selection was done. And we just move to the 0 position in the second line, and we just print the content of the buffer, and that's all. And this is done with all the variables which correspond to a menu item, so acceleration, number of turns, and so on and so on. And as you can see, whenever these variables are true, then we put that small larger symbol there. Otherwise, if we are in the else part, so that is when we press the button, we exited the menu, and one of these variables became false. So this is when any of these variables are false. Then we just print 2 spaces here. So basically this symbol will be erased. And then that lets the user know that now we are in the main menu, so we can navigate around in the main menu. So then I skipped a few functions here, so I just jump back to that. So this is the update menu position. So what happens here is that we erase the whole screen, we don't care, and then based on the menu counter with this switch case part, we print something on the display. And here I'm not going to go through all of these because they are the same, but what happens, I select a font, then I erase the previous text, but since I deleted the whole screen, this might not be necessary, but let's stay on the safe side. So I erase the text in the 0 line, and then I am still in the 0 line and print speed. Then I increase the font size, so I select another font size, and then I create this buffer with the stepper max speed. So I store this 8-bit large buffer in a decimal format, and I store this number there. And then I go to the second line, to the 15th pixel, and then I print the buffer. So basically the stepper max speed. And then this is done with all of these different cases. So then we know that this is the acceleration. So we write acceleration on the menu, on the top line of the display, and we print the variable. And everything is basically the same, but here the selected part is a bit different in a sense that if you are planning to print a floating point number, you have to use the D to strf. So what we do is that we use the float, and then we know the number of digits and so on. And we want to put this in the strtemp variable. So this was a character array. And now we have this strtemp, which we can use in this snprintf function. So then this strtemp as a string will end up in this buffer, and then finally the buffer can be printed. So then these lines, this D to strf, are very important when you want to print a floating point number. Otherwise, if you put the wire diameter directly here in the snprintf, it will not work. So this is the same. Yeah, these are not really different. We just read the position of the main shaft stepper and the feeder stepper, and then we print that. And this is just basically a normal menu, as you can see. And then we have the update value. This is very similar to the previous one. So what it does is, again, a switch case part based on the menu counter. And now we are just focusing on the value. So this will not write, for example, here the speed again to the top line, or to the first line of the display, but it will only update the relevant part where we print the value of the variable itself. So that happens in each line, as you can see. And the last menu is a bit more complicated because we have several lines where we want to update different variables. But I put some comments here. So in the line number 2, we have the layers left, and then the turns left in the number 4, and in the number 5, we have the consumed wire lengths. And then the strategy is the same. So we looked at this update selection. So let's see what happens if the up button is pressed. This is again, it's a polling based reading, not interrupt based. So we poll the button in every step of the, or every iteration of the loop. And whenever the up button becomes 0 and the time between two button steps is larger than 300 milliseconds, we go here, this part. So let's see what happens here. So if we are in the speed selection menu, then we increase the variable by 40. Same happens with the acceleration. In the number of turns, it is 10. The bobbin width is 1. Bobbin diameter is also 1. And then if the winding is selected, then we actually start the winding, because the up button is the start button as well. So if we are in the winding menu, what happens here is that we set the current position of the stepper motors, regardless of their current position, to 0. So we say that this will be the origin. And then we calculate the speeds which are necessary for the movements. And then, based on those, we tell the main shaft to move the total steps minus 2 times the main microstepping. And why we put this part there is because we already wound 2 full turns on the coil manually to start the coil. So then we don't need to move that 2 extra turns. And similar happens in the feeder. So we go and say that we have to move 1 layer equivalent of displacement minus 2 times wire diameter times feeder microstepping divided by 5. So basically this tells the number of steps, which is equivalent to 2 wire diameter width. And then this just instructs the feeder stepper motor to just move one layer, and then the additional layers will be managed in another function. So after we instructed the 2 stepper motors to move a certain amount of steps, we just set up their speed, and then we make the winding running through. So that's all. And then we can manually move these feeder and main shafts. And how it happens is that whenever you press the button, then we have this variable. We read the current position of the stepper motor and we add 160 to that position. And we store that in the stepper button steps. So we maximize the speed in 400. Maybe this is not necessary. I just kept it as this. And we tell the motor, or tell the code, to step the motor by basically this amount of steps. And then the same happens here in the feeder, but the feeder is stepped with a little bit less steps. But in both cases we have like 0.1 as the unit, or 1/10. So 160 is 0.1 times 1600, and here we have 0.1 millimeter, and if you have 320 steps done, that is 1 millimeter. So this is why I chose 32. And then if we do the down button, then basically the same happens. So we read the button, and if it's 0, we let the code enter here if there was no any button press in the last 300 milliseconds. But then we do everything in the other direction, so we decrease the values or stop things. So here, if the value of the stepper max speed is above 40, then we let this value to go by 40 downwards. But maybe this should not be 40, but should be 80. So 40 would be the minimum, but this is fine. And then we do the same with the acceleration, same with the number of turns, and so on and so on. And then when we reach the winding part, then we disable the winding partially, at least, by setting this to false. And then we use the stop functions to stop the main shaft and the feeder as well. And then when we want to move the main shaft or the feeder shaft with buttons, then the same happens as it happened with the up button, except we are moving in the negative direction now. So we subtract the numbers. And now comes the more fancy part, which is the calculation. And first of all, I just show you the code, and then I quickly also explain the calculations. So we need the total amount of steps for the main shaft, which is based on the number of turns and the microstepping for the main shaft. And as you can see in the code, I left an example everywhere, and hopefully my calculations are okay. And then I use these 2 lines just to send the values to the computer so I can see and check if they are calculated properly. Then we want to know the turns per layer, which is basically the relation between the bobbin width and the wire diameter. Then we want to know the number of layers, so that is the ratio of the number of turns and the turns per layer. So then you see the example again. Then we want to know the layers to do, and that is basically the number of layers, but the layers to do is a dynamic value, as I mentioned it earlier. So this will be actually changed during the operation. Then we have the feeder shaft total steps, which is based on the number of layers, the width of the bobbin, and the number of steps equivalent to move 1 millimeter with the feeder. Then we have the steps per layer for the feeder, which is a ratio between the feeder shaft total steps, so the total steps which are supposed to be done by the feeder, and then the number of layers. And then finally we have to calculate the speed for the feeder, And how that is done is that we divide the maximum speed of the main shaft stepper by the main microstepping, and then we multiply this with the feeder microstepping and then the wire diameter and divide it by 5. I will show you how this works. So then let's look at the check steps function, and what we have here is basically an if condition, and this determines if we can do something or not. So if the winding is running, so if this variable is true, then we enter and look at the next if condition. So this means that if there are no steps to go for the feeder, then we enter this part. And what we do here is that if there are still layers to do, then we run the winding function, and we also update the value on the display, which is basically just the recalculated number of turns and the consumed wire. So then if we still have to do layers, we do it, and then we also look at the main stepper. So why? Because first of all, this function tells if we ran out of steps for the feeder, but it can happen that that was the very last step, so we also ran out of steps for the main winding motor, which turns the shaft for the bobbin. And then if that is the case, so if this is 0 also, the main shaft is finished, then the winding is running is false, so we will not enter this part again with the next iteration of the loop, and we calculate the final amount of wire for the consumption. And I will explain this in the video how it works, but basically we just look at the number of turns left, and then we use the 2 pi, so I just simplified it, and then this is basically this big part of the equation here is just the large part, which is just the radius with the different corrections, and then we divide it by 1000 because we want to show the value in meters. And I also took the liberty to define square root of 3 like this, so I don't want to calculate square root with the microcontroller. And after the wire calculation is done, then we update the value on the display, so the user knows the final numbers. So then here we saw this winding function, so let's look at that. So first of all, when the winding function is called, we calculate the total wire length, or this is just a part of a wall sum. But what happens here is, again, I will show it later with some illustrations, but we take the turns per layer times 2 pi, and then this big thing here in the parentheses is just different radius contributions. And then after we enter this, we subtract 1 from the layers to do variable, and we also flip the direction. So if it was +1, now it becomes -1. If it was -1 when we entered this, then it becomes +1. And now we look at the numbers of layers which we have to do in this highlighted part. So if we have multiple layers to do, what we do here is that we call the move function, and what is inside the move function is basically the direction multiplier times the steps per layer for the feeder. And since there are multiple layers to do here, we can move a full bobbin width with the feeder, but I have minus here because I don't want to cover the exact width of the bobbin. So this is a bit empirical value, this 2 times multiplication. Maybe more is needed, in fact, to properly cover the wire in the higher layers. So then we pass these numbers or this calculation result to the move function. We also set the speed for the feeder. So then we look at this function. When the layers to do equals to 1, that means that we are making the last layer. And what happens here is that we again look at the direction multiplier, and then wire diameter times the amount of steps needed to move the feeder by 1 millimeter. And then this is sort of a correction factor. So basically what this part tells us is that here we calculate the number of turns done so far and subtract it from the total number of turns. So it tells us how many turns are needed to be done on the last layer. And then the number of turns times this amount will actually tell the stepper motor that we need to step this much amount. And then this is passed to the move function. And then finally we set the speed again. And then if none of these are fulfilled, then the layers to do is 0. So we finished with everything. So we don't do anything inside this function anymore. And this was the programming part. So now I will show you some kind of slides and explain the calculations in more detail, especially focusing on this function, the calculate speeds function, and then, which is a bit more tricky, the total wire length. So I will explain these things to you. So the total steps of the main shaft is the first thing that we calculate in the code. So what happens here is that we take the number of turns, which has the turns as a unit, or we can even consider it as unitless, and multiply it by the microstepping. And why do we do that? You can see it in the example. So if we have 160 turns, that means that the main shaft has to turn 160 times. And the microstepping is defined in a steps per turn unit. So then we just have to multiply these two numbers, and we have these 256,000 steps. Because 1,600 steps will do one turn, so then we want to do this turn 160 times, so we just multiply it, and then yeah, we got this number here. So what happens here is just this command or this number will tell the main shaft stepper motor to move this much steps, and we move the main shaft without any kind of interruption. So these 256,000 steps will be done without any interruption. Then we have the number of turns per layer, and that is the bobbin width in millimeters divided by the wire diameter in millimeters. So in my example, this was 14 millimeters and the wire was 0.35 millimeters. So if you divide 14 by 0.35, you get 40. So in one layer, you will get 40 turns. So basically, we have the bobbin. It looks something like this, and that has a certain width. So this was the 14 millimeters, and then we put the wires here, basically something like this, and then each wire increases the width of the coil here. And finally, if we use the 14 millimeter wide bobbin, like here with the number, and these wires were 0.35 millimeters, then we can fit 40 turns or 40 pieces of wire next to each other. So this is also very simple. Then we have the number of layers. So we know the total number of turns, which is a user input parameter, and then we know the turns per layer, which I just showed you in the previous slide. So for example, if we have 160 turns and we can fit 40 turns in one layer, then we have 4 layers. And this number is always rounded up. And I try to draw it again very quickly. So we have the bobbin here, and then we start to put the wires on it. So we complete one layer, and then we complete another layer. Let's make a third one, but let's make a fourth one, but that will be like a partial layer. So we will not complete, let's say, these numbers, but just 135. So this fourth layer is still there, but it's not not a total layer, because this part is just empty space. So we have 3.5 layers, but that is from this kind of calculation perspective, it is still considered as 4 layers. So this is a bit more longer equation, but still it's relatively easy. So we want to know the total steps for the feeder, and this will help us to calculate the number of steps for the full layers. So when we have a full layer, when we fill in the total width of the bobbin, then this number will be used there. So we have the number of layers, and then we multiply this with the bobbin width, and Then we multiply that with this number, which is the feeder microstepping. This can be 1600 as it is in the example, divided by 5 millimeters, which is the screw or ball screw pitch. You see the units here. And then this is 17,920 steps. So the stepper motor would move this much if we would use, let's say, optimal numbers, because actually these numbers that I'm using, they fill up the coil perfectly. Then we have the steps per layer for the feeder. So we use the feeder total steps, which we just obtained in the previous slide, and we divide it by the number of layers. So as you can see, this 17,920 is divided by 4, so we have 4,480 steps. So this gives us the number of steps for a full layer. So if we have the bobbin here once again, and for example we have the full layer full of wires, then the stepper motor will have to do 4,480 steps in order to complete the movement starting from here and going to here. And then, as I explained, we just fill in a few other layers here, and then we have the final layer. And it can happen, and I think that can be quite usual, that the final layer is not a complete layer. Then these steps will be not valid there, because of course if you would use this amount of steps, then the nozzle of the feeder, which is, let's say, this arrow, would actually continue its way until it reaches the end of the bobbin, and this can be maybe several centimeters, and that could mess up your coil. So the last layer's steps has to be calculated somewhere else, and that will be done, and I will show you how it's done. Then we have the feeder speed, which is a bit more let's say critical to know. So this will depend on the speed of the main shaft. So what we have in the first term here in the parentheses is the main shaft speed divided by the main shaft microstepping. And then we multiply this by the feeder microstepping divided by the screw pitch. So basically this part tells us how many steps are needed to move 1 millimeter with the feeder. And then we multiply this by the wire diameter. So in the example you can see what happens here. So the 1600 steps per second, this here, divided by the 1600 steps per turn, this one here. And then that is multiplied with this part, which is 1600 steps per turn divided by 5 millimeters per turn. And then that finally is multiplied by 0.35 millimeters. So the final result after taking care of all of these unit dimensions will be 112 steps per second. So that will be the speed of the feeder. And I wanted to double check these calculations. So we know that one layer is 4,000, one full layer is 4,480 steps. So then if we divide this with 112 steps per second, then we know that it will take 40 seconds to complete one layer with the feeder. So that is said here. And we know that we have 4 full layers because this example uses 160 turns, which is 4 layers. So then we know that if one layer is 40 seconds, then we just multiply it by 4. So 160 seconds is needed to complete the 4 oscillation basically. And that we know. So then we also know that the main shaft speed was set to 1600 steps per second, which is also happened to be 1 turn per second. So then we know that if we have 1 turn per second and we have 160 turns, as it is shown here, then that is also 160 seconds. So the main shaft and the feeder goes with the same speed now, so they are synchronized nicely. And also we know that 320 steps on the feeder is equivalent to 1 millimeter. And we also know that if we divide the 112 with 320, we get 0.35, which is the wire diameter. So we also see that the feeder moves with 1 wire diameter per second, which we actually want. So this is also like a good checking. So now we have one of the more, let's say, complicated equations, which is the number of feeder steps for the final layer. And how it's done is that we take the wire diameter, 0.35, we multiply it with the 1 millimeter equivalent of steps, and then we multiply it with this longer term, where I left out a few parentheses. But what happens here is that we take the number of turns, which is in this case, I used something which is not a full layer turn. So I used the 135 here. And then we know that we still have 4 layers, so actually this term becomes 3, and then the turns per layer was still 40. So you see the calculations down here. So 0.35 millimeters times 320 times, in parentheses, 135 minus 3 times 40, so minus 120. So actually this term becomes 15 at the end. So then the whole thing becomes 15 times 320 times 0.35, and that is 1680 steps. So this will be the number of steps for the feeder for the final layer, if the final layer is not a full layer. But of course you can see it here that if it's 160 here, then this is still 3 and this is still 40. So we basically just do this. And then this is a full layer equivalent of turns. So then finally we have arrived to the probably most fun part of this calculation. So here I want to calculate the total consumed wire length. So there is a little trick here which I will show you step by step, because it's not simply just multiplying the number of layers with the initial diameter, because the diameter of the coil is constantly growing layer by layer, and we have to account for that. So I came up with some kind of formula which takes care of this and which is treated in the software as well. So on the left side here in the corner you can see that we have 4 layers, and first of all this L and this L here is not the same, so sorry for the confusion, but we have 4 layers, and you can see that I put a line to each layer's center, which will help us in guiding through this thing. And then this box here is the bobbin. So this is where we coil up the coil itself. So if you want to calculate the circumference, then you have this formula, 2 times r times pi. So where we have this coil, we constantly have different r with the increasing layers. And here, let's say that this is the center of the bobbin. So the first r, at least I consider this as the first radius, is between the center of the bobbin here. So let's say that this is the center, and the center of the first layer. And this is one step. And how this is made is basically we take the r, or the radius of the bobbin, so rb, and then we take the radius of the first layer. In this case that's the wire, so rw. So when we have a full layer, so that is for example the full first layer, we have the turns per layer here, as you can see, and then we have the 2 pi from this circumference formula, and we left with the r. So what we see is that we have the r bobbin plus the r wire, and then if we are in the first layer, then we stop here, so we don't consider this formula. But this actually is being neglected, because what we have here is that the L, which is now this L, is 4 in this case. Check this line here. So the L is 4 here, and then we have the small l, which is also 4, because we still have 4 layers to complete. The first one, of course, when we look at this formula in the code, then the first one still has to be completed, and then we have the 3 others, so 4 layers has to be completed. So actually this product is 0, so then this is also 0. So what we have left with is, when we are in the first layer, is that the 40 turns times 2 pi times the bobbin radius plus the wire radius. So basically we can stop here. And that is 2.56 meters. And then we move to the next layer. So what we have in the next layer? So first of all, we have the RB again, and then we have the R wire again, and then the center is this line here, which I call X, because we don't know, because what we have here is not the 2 times the wire radius, but something else. And for that we look at this part down below. So we have one layer here, as you can see, and this is the next layer, and we are looking for the X here. And I just highlighted this right angle triangle and put it here, and what we have is that this line here is the X, so basically this part here, and then we have the radius here, so the radius of the wire, and then this larger line, this is basically, you have an R here, this part, and then this part is another R, so then this is 2R. And then, if you are a bit familiar with material science, you can recognize this kind of stacking or packing sequence, which is the hexagonal closed packed packing. So basically you have A, B layers on top of each other. And when you calculate the lattice parameter and the atomic radius and these kind of things, you are using similar approach. So what we have here is we have the 2R, and then we have the R, so these two values are known, and the X is an unknown. So we use the Pythagorean theorem in this part here, and then we just rearrange for X. So at the end we have this 2R squared as 4R squared when we open up this parenthesis, and then that brings us to 3R squared equals X squared. And then we just take the root of this, the square root of this equation, and then we get square root of 3 times R equals X. And if you are a nitpicking mathematician, and if I'm not wrong, then this should be in absolute value, of course, because if you take the square, that can be a minus number as well, and you end up with the same number. So when you take the square root, it's plus minus, so it's in an absolute value, but this is just for fun. So then we know how the X is obtained, and the X is always square root of 3 times the wire diameter. And to simplify the calculations in the microcontroller, this is where I used 1.732. So instead of calculating the square root of 3 inside the microcontroller, I just use this number because we don't need that much precision, and this 3 digits is more than enough. So now we know the X, so we can go to the second layer and calculate the increased diameter or radius of that particular layer. So we are in the L equals 3. So now the first part of the equation is the same. So the turns per layer, since we have a full layer here, is 40 turns. That's fine. 2 pi comes from the circumference equation. The bobbin diameter is still 10 millimeters, and then the wire diameter is still 0.175 millimeters. But then this capital L minus L part, this part becomes 4 minus 3, because 3 layers are left to complete. The second one, the third one, and the fourth one. So then we multiply this 1 with this equation here, so square root of 3 times 0.175, and now we get a slightly larger length, so this is 2.63 meters of wire. And then we move to the third layer. So again we have the bobbin radius, and then we have the radius of the wire, and then we have the x here, and then we have another x here, so 2 times the x, and that comes from the equations as well. So what we have here is 40 times 2 pi, that's fine, because still we have a full layer here, let's say. So then this is the bobbin radius, sorry, then wire radius, and this is 4 minus 2, because 2 layers are left, the third one and the fourth one. So then this is 2 here, so we take this number twice, and now we have a bit larger length again. And now we reached the last layer, and for the last layer I said that what if we don't have a complete layer, so we don't go from one end to the other end of the bobbin. So what happens here is that I took 135 turns as an example. So this would mean that the fourth layer would stop somewhere halfway or a bit more, but it would not complete the full 40 turns in the last layer, because we don't have that much layer. So I had to come up with another formula, and I added this term to the final length formula, which means that we take the total number of turns, which is given here, 135, and then we use this turns per layer, which is 40, and multiply it by the completed layers, basically. So the layers in total minus 1, so this becomes 3. So this equation actually will tell you the completed number of turns in total, and this is 120. So actually this equation in the parentheses in the beginning of the equation is 135 minus 120, so it's 15. So what we have here, that instead of 40 we have 15 times 2 pi times the radius of the bobbin plus the radius of the wire, and then we have 3 times the x. So this is 3, because what we have here, now I have a bit more simplistic drawing, so bobbin radius, and then we have the wire radius, and then x once, x twice, and x 3 times. So then this is the x here, so then we have 3 times x. But since we have just 15 turns, then that's less than half of the original number of turns, and then here we get less than half of the previous number, which seems to be correct. So about 1 meter of wire is needed. So then, if I haven't messed up my formulas, this would be the last slide, and hopefully all the formulas are correct. So I hope that you understand this wiring and winding a bit more in detail, and you see how the wire consumption is calculated, how the speed, how the steps are calculated, and with this you can make your own coil winder, or you can make something which works with the similar principles. So I put all the resources on my website, curiousscientist.tech, so please don't forget to visit my website. There is a lot of extra things which you can find there. So I hope you learned something. I hope this video was helpful to you, and see you in the next video.